Good morning, Year 12. How's it going, guys? Sian's first person on the no, sorry. Shaz is first on the chat, I believe, saying hello. Sorry, guys. It's having a few computer issues there. The monitor decided to suddenly turn off. I've plugged it into a different plug socket, and it seems to have come back to life. It's very odd. Let's crack on, guys. Share screen. So today we're looking at calorimetry. Let's get rid of me. Right, I'm just making sure that, yeah, that's really odd. Perfect, that's all up and running, that's fine. Right, hide that, let's crack on. So today, guys, energetics lesson 6 for AS, and we're looking at calorimetry. So we've finished looking at bond enthalpies, we finished looking at Hess cycles from a combustion standpoint, from a formation standpoint, and from an unlabeled data standpoint, and now we're entering into the practical aspect of energetics. So calorimetry, 4 learning objectives. Know the 2 types of calorimetry. We've already discussed this right at the beginning of energetics, but I'm going to cover them again. Know both equations. So these are the equations that you're going to need to use for calorimetry, and I'm going to show you some questions which kind of take adaptations to those. Then know calorimetry problems, and then be able to access exam questions, which I have on hand here, and we will have a look at some of those once we get towards the end of the lesson. So, okay, first things first, what is calorimetry? So, calorimetry, a practical to determine the heat energy change, of a reaction. Okay, so we remember these from GCSE. There were 2 types of calorimetry. There is internal calorimetry, and this is the better of the 2. Yeah, internal calorimetry. I'm going to put underneath it best. Yeah, and then we have external calorimetry. And the reason why you've got to subdivide these, now you're not going to find any writing about these being subdivided. This is worst. It's terrible. It's the most disastrous practical ever. Just gives you horrible results. Are just nowhere near what it's meant to be. But you need to understand both of these because they have different. This is where the calorimetry problems subdivide. Yeah, because they have very different issues, and we have to look at each one of them independently in terms of their problems. Okay, so let's draw these out. Let's do internal first. I'm going to switch my pen to being skinny. So internal calorimetry, polystyrene cup. Yeah, and you can label this polystyrene cup. Insulation, we know this. I'm going to put insulation. Yeah, we often actually then put this in a beaker. We often put this actually in a beaker to act as support. It also acts as another layer of insulation as well. Yeah, so this is a beaker. It also acts as stability because it stops it from falling over. Yeah, and then we often then have a lid as well for this. I'm not going to add the lid. I will. I'll add the lid. I'll add the lid. And then running down through the lid would be our thermometer. Yeah, so lid. Now, can I just point out and then our thermometer. Can I just quickly state that one of the key things here for improvements is the lid. You can just circle the lid, and this is often missing. Yeah, often missing, and it is a clear improvement. Yeah, this is a prac improvement. Add a lid. Prac improvement. Very, very common. Yeah, prac improvement, add a lid. So the idea behind internal calorimetry, why is it called internal? It's called internal because the heat energy of the reaction is occurring inside the beaker. That's why. Yeah, so inside here, we will have a solution perhaps. Yeah, a solution of something. Sorry about the quality of my sketch. It's not great, is it? And then would be a reaction going on between these 2. Yeah, and this is going to be generating the heat. And the heat the heat source. Heat source. The heat source is inside, and that's the internal bit, inside the calorimeter. Calorimeter. The calorimeter, technically, by the way, guys, is the polystyrene cup. Technically. But it's inside the reaction. What this means is less heat loss. Yeah, less heat loss. Not only that, but, and you can add this for see next lesson's notes, see lesson 2 on calorimetry's notes. I'm not going to bother doing that. Yeah, heat loss can be accounted for by using graph. That's really important for A-level. That's the A-level step up, really. You've done internal calorimetry before at GCSE, but you've never done this bit. This is the A-level extension. My pen seems to be hiccuping. I wonder whether or not the battery's dead. Ooh, we'll see how it goes. So what does external calorimetry look like? External calorimetry looks like this. Copper calorimeter. So this beaker, and this is not a beaker. Yeah. Shouldn't call it that. It's a calorimeter, and it is usually made from copper. Yeah. The reason being is copper is a good conductor of heat. Yeah, good conductor of heat. Let's add that to our notes. Yeah, we've got good conductor of heat. Conductor of heat. However, it will absorb some. So this actually flags up as a problem as well. Isn't that funny? It's both a good thing and a bad thing. Yeah. Copper does absorb some heat. Does absorb some heat. Some heat energy. Heat capacity. Heat capacity used in equation not correct. Yeah, it should actually be an average of the two of them, and that would be complicated to do. But we've got a copper calorimeter. We're going to fill it with water. Yeah, we're going to fill it with water, and this is simply to capture the heat from the reaction outside, from an external heat source. So this is most of the time used for like a combustion perspective. Let's see if I can do this well. I'm going to do this really badly. There we go. So this is a burner. This is a fuel burner. There we go. And the source is therefore outside. So this is our fuel burner. Yeah. And what we're going to do is we're going to light this, and we're going to measure the heat output. Yeah. We're going to measure the heat output of this thing. Yeah. And you can see that the heat source is outside the calorimeter. Yeah. So that's the difference. Yeah. Let's put a stand on there. Why not? Okay. So, and this is why it's called external. Fuel burner. I'm going to draw an arrow from there. An arrow, don't like that, green. There we go. Heat source outside of calorimeter. Calorimeter. So if it's outside the calorimeter, this is external. Yeah, an external heat source. And this lends itself to massive heat loss. Problems. Massive heat loss. Massive heat loss. Huge heat loss. Yeah, and there are things that we can do to reduce it, and we'll talk each one of those through. But this is just where we're looking at this at the minute. We just wanted to see what the difference is between internal and external, realizing how bad external is The heat loss is massive. In bio last year, there was a question about some sort of an upgraded calorimeter, which still uses combustion but worked way better. Is it possible we might get a similar question in A-level? Yes, it's called, so Oliver, it's called the bomb calorimeter. Now, can I just point out the bomb calorimeter? Ugh, nota bene. Yuck. Nota bene. Bomb calorimeter. Now, here's the thing. You need to know of it. Bomb calorimeter. Does this ring a bell, Oliver, by any chance? Yeah, bomb calorimeter. There we go. Bomb calorimeter. Images. There we go. Yeah. So the bomb calorimeter is a very expensive device. I've only ever met one of these once in my life. They weigh a good 300, 400 kilos. Yeah. But the thing is, you can't say what they're going to do in your exam. So the bomb calorimeter is an improvement. We designed this because it has huge amounts of insulation. It's designed to minimize the heat loss and so give better answers. But the thing is, you're never going to actually have access to one. So the question might be, a student, if a student uses a bomb calorimeter, why would it be better? And you would simply say less heat loss. That's it. Yeah, and it's a bit of a nightmare, really. You can kind of, but what you can't say is that, oh, state how a student can improve his method, and you say use a bomb, you can't do it because you don't have access to them. They're about £100,000 to boot as well. Yeah, so we'll come to that. We'll see if we can find any questions about them. Right, next. So we've covered the two types today so far. Next, the two equations. Now, because this is a practical, oh, come on, laptop. There we go. Right. So, title, calorimetry. Uh-oh. My pen is hiccuping for some reason. I'm going to fix that. Calorimetry equations. You had these at GCSE. Is hiccuping. Calorimetry equations. First one, now at GCSE you were always given this. You are no longer going to be given this at A-level. Q equals MC delta T. Now this equation is entirely about water only. This is about the water, not the fuel. Bear that in mind. So what does each bit stand for? Q is raw energy. Raw energy and has a units of joules. M is the mass of water. M is the mass of water. Next, C is the heat capacity. Heat capacity of water. Yeah. Q is the temperature change. Temp change of the water. Yeah. This equation's super important. Now, can I just tell you something here for a minute, which is something you definitely weren't taught at GCSE. There is another version of this equation. Yeah. And what they do is they call it the overall heat capacity. So what they can often do is just, this is a nota bene. Nota bene, M and C, MC, the mass, and the heat cap can be combined into overall heat capacity. So I'm just letting you know here, just to show you this in action. Look, in this particular exam question, a vessel and its contents of total heat capacity, right? That there is M and C put together. Yeah, it's a bit of a nightmare, this. Yeah, so it's something just to bear in mind. The overall heat capacity, or sometimes referred to as total. I'll actually write down what the exam paper actually said there, actually. So this is total heat capacity. So just watch out for that one. Once you've got the first equation, which is all about water, yeah, the next equation you have is delta H equals Q over N. Now, this equation is commonly not taught at GCSE, which is really irritating. This is the enthalpy change, what we're trying to find. Yeah, that is usually the question, but not always. Bear that in mind. Yeah, not always. It's usually what we're looking for. Now, here is a nightmare. In this equation, Q is energy, but it's in the form of kilojoules. What that means is that there's a step between these two equations. This here is step number 1. This is step 1. Step 2, however, yeah, step 2, I'm going to change the thickness of my pen there. Oh, still not what I want. Step 2 is to divide that answer by 1,000. Yeah, because when you run Q equals MC delta T, it's going to spit you out in joules. And then you can bring it up to this guy for step number 3. Yeah, that's step 3. Just bear it in mind. Yeah, step 2, step 3. Okay, so Q is energy, and now this one is moles. Yeah, this is moles. And this is moles of reactant. Yeah, so that might be moles of fuel. That might be the moles of fuel. Or it might be so this is going to be external. Yeah, but it might also be, this also might be the moles of the solution. The moles of the solution, or the substance in the solution, depending on who's in excess. Yeah, this one here has an extra clause, which is ignore excess reagent. We know that one. Yeah, we know that. We always ignore the excess. So anyway, so we pick up our three steps, but 2 equations. And we make this extra leap to A level with that point there. Right, let's go to the next one. So calorimetry problems. Now, what I'm actually going to do is, for Q, is the units for mass kilograms or grams? It's grams, Oliver. I know what you're doing. You're realizing that in physics, they give you the heat capacity in kilograms, which is stupid, by the way. Oh, physics. For the delta H, is it for specific substances like the one for water? For delta H equation, is it for a specific substance? The delta H one, yes. You're realizing now the step 3 is about bringing it into the fold of the reaction. Kilograms using grams is, oh, no, Oliver, no, I don't care that it's the base unit. The fact that it's the base unit is the stupidity. Don't even get me started on this, Oliver. Just don't. Who thought it was a good idea to measure everything in kilograms when all the chemical reactions and even the physics demonstrations you're using grams? Why would you do that? No, just no, Oliver. Physics is stupid using kilograms. They never even use it. Oh, don't even get me started. Don't. Oh, I'm not even. He's ruined my lesson. He's ruined it. Right. Oh my God, I'm so angry with you right now, Oliver. So angry. So, going back to this, let's talk about some of these common problems. Let's do it. Let's do common problems. So, common problems. I think my pen is on the way out. I just need to recharge the battery. Common problems. Common problems with calorimetry. Common problems. Okay. So, common problem. But these kind of, you do this like family fortunes, guys. I'm so angry with you, Oliver. My brain is reeling off it. I don't like it. You've upset me. Common problem number 1. Our survey said, number 1, top answer, heat loss. Heat loss to environment. Now, that is the top reason why it's such garbage. Yeah. However, I'm not going to lie, they're going to take that one away from you. They're going to say, excluding heat loss, give a problem with this calorimetry process, they're going to remove it. You'll see this in the questions. Number two, an incomplete reaction. I'm just going to say incomplete reaction. Incomplete reaction. So the reaction didn't finish. Yeah, very, very common. The reason being is a lot of times, you know, if you're using a solid, for example, this is very important because what's going to happen is for the solid to completely be reacted, it has to be turned into like a soluble product or something that will dissolve into the water. And it may not do that. There's usually stuff left over, stuff that doesn't react. Number 3, side reactions. Side reactions. So we're getting, one reaction. So for example, in external calorimetry, yeah, we're burning the fuel. Now we have to make a massive assumption that the reaction is going to be complete combustion, and it's not going to be. This is one of the biggest problems with combustion analysis, because in reality, if we take a fuel, let's take ethanol, for example. Yeah, this is an EG of side reactions. EG side reactions. If I take ethanol, CH3CH2OH, and I burn it in oxygen, I have to assume for calorimetry that I'm forming CO2 and water, but that might not actually be the case. Yeah, let's balance it. I've got to balance it. 7-3, I think. Something like that. But in reality, there's another reaction going on. I'm also going to have that reacting with oxygen. I'm going to do this in a different color. Yeah, it's also going to react and make it a bit thicker to join the other one. It will also react with oxygen and form CO and water as well, incomplete combustion. Well, there's also going to be a third one. We'll also have it reacting with oxygen to make carbon and water. We're getting side reactions here, the incomplete combustions. What that means is we're never going to get the output we expect. Yeah, this is a nightmare. So side reactions. Number four, the reaction could be reversible. Now, I don't really want to add that one to the list, to be fair. I've changed my mind on that. It is a reason why we don't get the heat, but it's also to do with really much to do with the outcome rather than anything else. Okay, let's skip that one. Let's go to impurities. Impurities. That one quite often gets taken away from you, just so you know. Impurities in reactants. Like it. Incomplete reactions, side reactions, impurities. Heat loss to the environment. Are there any? Incorrect heat capacity. Yeah, number 5. Incorrect heat capacity. Heat cap. We are heat capacity. So the reason being for this is if you have a copper calorimeter that you fill with water, and we are then heating, what we realize is we're taking the heat capacity of that. The C of water is 4.18, yeah, or 4.2 for you guys, I believe now, but 4.18, and that's per grams, Oliver. So that's 4.18, but in reality, the copper is also absorbing some. Yeah, so the copper on the outside also has its own heat capacity, which is usually much higher, but it's also a good conductor, so it passes it to the water quite well, but it does have a separate value. I'm tempted to look that up. What's copper's heat capacity? You guys might even know. Copper heat capacity in joules per, look, they're even quoting it in joules per gram. Yeah, Oliver, yeah, in your face. Joules per gram per Celsius. Yeah, so for copper, it's 0.385. Isn't that interesting? Why is it so low? And what? That's interesting. 25 more. I want to see water. There you go. 4.18. That's really interesting. Copper's is very low. which is interesting, isn't it? It's telling you because it's going to lose the heat, it's going to conduct the heat away really well. Isn't that fascinating? Doesn't hold much. Huh, didn't expect that. So 0.3, it also realizes, well, if looking at what was the number, 0.385, it's really nice to know that because it tells me that in reality, the difference is marginal. It's actually a very small difference, isn't it? So it's not going to be one of the top reasons for loss. Yeah, the water is catching, 10 times as much heat as that can per gram. Yeah, but anyway, lots of reasons for these. Now I'm going to start, now that we've discussed these problems, what we can now do is start looking at the exam questions. And this is important just to get straight into it. Okay, so what I'm going to do is this is just a database of questions on energetics, and I'm going to pick out all the calorimetry questions in this situation. So, okay, I'm going to do this one straight off the bat, full screen snip. Guys, if you want to get mad at people who choose kilograms, blame the French, not the modern day ones, though. The dead ones who made up the units. So why are you defending them, Oliver? Why are you telling me that the chemistry is the stupid one when you've just then said that the stupid one is the... Stop talking to me, Oliver. You're cut off. Right. Guys, can you please pause the video and can you have a go at this question now? 4 marks. Pause the video. If you really have no idea, don't worry, you can follow me through it. Okay, so a vessel and its contents have a total, right, there's MC. And we're heated using a methane burner. Calculate the maximum theoretical temp. Oh, that's interesting, isn't it? We're calculating the temperature rise, not the delta H. And they've given me the delta H. They're making me go backwards. Look at that. So straight away, I'm going to write down my 2 equations. Q equals MC delta T. What I'm after is the delta T. And I have been given this. Yeah, but I don't have Q. But the second equation, delta H equals Q over N. Right, I do have a delta H because it's here. That there is delta H. Yeah, delta H. And I do have grams of methane, which means I can work out moles. I do need to remember that if the one of them was divided by 1,000, then this one's going to be a times by 1,000 in the opposite direction. Got to watch out. It's all a trap. So let's run it through. Reorganize that for Q. So my first mark will be that reorganization. So I'm going to bring the N over. So Q equals N times delta H. Right, so now I've got my equation, that's 1 mark. I need to work out the moles. And I had 10 grams of methane. Right, so number of moles is grams over rams. Number of moles equals grams over rams. And I have got, therefore, grams is 0.10 grams over the MR of methane, and methane is CH4. So that's going to be 12.0 plus 1 times 1.0 times 4. So the answer there is 16.0. Now, guys, can I please reminding you, year 12, you are not allowed, please stop doing this. Yeah, please stop it. That is not a mark. Stop doing it. Yeah, throwing marks away. And don't forget your 1 decimal place. There's your 2nd mark. Yeah? Right. Now we're going to get moles. So the moles of fuel, calculator, on 0.1 multiplied by, my calculator has just literally turned itself off. Fixed it. 0.1 divided by 16.0 gives me an answer of 6.25 times 10 to the minus 3. There's my moles. Right, run it through the equation. Q equals 6.25 times 10 to the minus 3 multiplied by kilojoules per mole. So that's interesting. Now, at this point, I get rid of the minus. You can't have negative Q. It's raw energy. So I'm just going to make that disappear. 890 multiplied by 890 equals S to D. Right, so my Q is now 5.5625, and that now is in kilojoules. Now I need to convert it to joules times 1,000, which takes me to 5562.5 joules. Now I can work out my temperature change. So there's my equation. Yeah, no. I need to reorganize this guy for delta T. So that's going to be Q over MC gives me delta T. So there's my Q divided by the total heat capacity of 120. And I get a temperature change of 46.4 degrees Celsius. Now here's the next bit. Is it going to go up or down? Yeah, the maximum theoretical, oh, it's already said it in the question, temperature rise. So there's my answer. I'm done, 4 marks. Where do the marks come from? 1, 2, 3, 4, probably. In reality, it's more marks than 4's even worth, isn't it? But what a great question, though. Love that. That's great A-level right there. Let's go for the next one, folks. So this one's dropping us into a cycle. Oh, nice to mention. State why the standard enthalpy of formation of lithium is 0. Yeah, the reason being is the definition of enthalpy of formation is the heat energy change when 1 mole of a compound is formed from its constituent elements. It's not a compound by definition. Isn't that a nightmare? It's an element. The answer to that question there are 2. You can either say it is an element in its standard state, 1 mark. Element, I'll say lithium, Li solid, is an element in its standard state. There's one answer, standard state. The other answer, state, come on, Mr. Duncan. Standard state. You are also allowed to say, by definition. I don't like it. They can take that away from you. And I warn you of that. But anyway. Write an equation. I'm looking for calorimetry. Oh. Write an equation that represents the formation of lithium hydroxide. Fine, we can do that. Lithium, water, hydrogen ions. Oh, write an equation including state symbols for the reaction with lithium with water in which lithium ions are formed. What a lovely question. Oh, don't want to write on that. No. Snip. Guys, this is really lovely. Can you put it in Kelvin too, or is Celsius better? Aggressive banging noises fixed it. Yeah, I just bashed it on the table and it's now working. Classic way of fixing electronics. It's so true. Oliver, the temperature change is the same in Kelvin as it is in Celsius. So you'd always quote it in Celsius because the change is the same. 1 degree change in Celsius is the same as 1 degree change in Kelvin. Right, so lithium plus, including state symbols. Lithium solid plus water liquid goes to form, now we know from GCSE, it forms lithium hydroxide aqueous and hydrogen gas. But they want you to show the ions. So we just separate who can be ions. So in this case, Li plus aqueous plus OH minus aqueous and hydrogen gas. And balance as necessary with a half. And you're done. Nailed it. Great question, by the way. Love that. Love it. Great question. Next, find the next calorimetry. Mr. Duncan, focus. Use the data given above to calculate a value for the enthalpy change. Don't care. Bond data, done it. Formation data, done it. Here's the next one. Right. 7 marks. An experiment was conducted to determine the enthalpy of combustion of liquid methanol. The energy obtained from burning 1.12 grams of methanol was used to heat 150 grams of water. The temperature rose from this to this. Define the enthalpy of combustion, the heat energy change when 1 mole of methanol is completely burnt in excess oxygen, forming CO2 and water only, all in their standard states and under standard conditions. Whew! Gotta know them. Use the data to calculate the enthalpy value for the combustion of 1 mole of methanol. Okay. I'm going to do it all in that tiny little space. By the way, this one's bog standard GCSE. Bog standard. Absolutely bog standard. So, 2 equations. Q equals mc delta T, and then delta H equals Q over N, and I just remember, divide by 1,000 when you're going like that. Okay, first thing. So what have I got? I've got a temperature change. Going to have to work that out on my broken calculator. 362 minus 298. Boom, 64 degrees. So Q equals, what was my mass of water? 150 grams of water, multiplied by the heat capacity, which they've given me, 4.18, multiplied by 64. The change in temperature there, that's 64 degrees. Right, run it through. 150 times 4.18 times 64 gives me 40,128 joules. Divide by 1,000. Straight away, don't even bother. Just divide it straight away. Yeah, S to D. That gives me 40.13 kilojoules. Like it. Now, going into this bit. So delta H equals 40.13 over the moles. We burnt that much methanol. Right, number of moles is grams over rams, 2.12 grams over methanol. What does methanol weigh? Well, I've got 12.0 plus 12 plus 3 plus 16 plus 1. And everyone's going to make a mistake because, of course, it's 32.0. If you forget it, you lose one. 2.12 divided by 32 gives me number of moles. 0.06625. Right, run it through. 40.13 divided by 0.06625. Yeah, S to D. Right, and I'm about to lose the mark. The reason being is you cannot, whenever you do this, you can't have negative energy. Yeah, kilojoules per mole. I'm going to move all of that bit there over. If I can, I'm just going to move all this. There we go. So there's the answer, but the problem is I'm still wrong. The reason being is because this is the combustion of methanol, and the temperature climbed. This is exothermic, which means you must remember to add your negative sign to your final answer. Yeah, that there, you've got to remember, is the minus sign because it means exo. Let's go for the next one. Go for the next one. Enthalpy cycles. Oh. I want to find one that's tricky. Magnesium. Oh. I'm being bleeped all over the place. It's because I've got another lesson. Right, guys, what I'm going to do is I will put together a booklet of all these. Propanone, 100 grams of water, fairly standard. Yeah. Difference in the data book. Oh, just to mention, by the way, difference in the data book. The data book is the fact that you can look up enthalpy values. Yeah? And I can do this here. We know that these reactions, these practicals, are garbage. Because of all of these reasons. So bad. Yeah? What that means is that if you compare to a data book has what are considered to be true values. True values. Ones that they have worked out using things like a bomb calorimeter. Yeah? But what we realize is that the data book value is always different from ours. Because no matter what we take, it's always different. So for example, with e.g. bond data, when you do bond data, which we did last lesson, we realize that the bond data is actually mean bond data. Yeah. What that means is the bond is averaged over a range of compounds. So it's slightly odd, slightly off from the true value. Yeah? And we get this quite commonly. And in this particular scenario, in a similar experiment, the combustion debris was found to be this. The data book, look at that. The data book is twice the size. Suggests one reason why the experimental value is very different from the data book. Heat loss, we're done. Heat loss to the surroundings. You wouldn't actually. With butanone, I'd say incomplete combustion. Top answer. It's a big alkane or big ketone. It's not going to burn completely. Anything above 1 is not going to burn completely. Anyway, I will leave you guys be at this point. I will post your homework, which are the tough calorimetry questions. We will go through those next lesson. Was there anything else I wanted to cover in my lesson? Where are my learning objectives? Exactly. So we've added in the list of the problems, but we'll apply those to questions next time. And we're going to look at exam questions next lesson. And then, guys, you're ready for your test on a week today. I will see you guys very soon. I will end my lesson there. I hope you found it useful. I will see you guys Thursday. Have a good day, guys.